Welcome, and thank you for choosing the Curious Owl. Tonight, you're invited to settle in and explore a gentle stream of knowledge, designed to be listened to without effort. There will be no advertisements during this audio, so you can rest without interruption. If you enjoy this kind of calm, thoughtful storytelling, you're welcome to like, subscribe, or share this video. It helps others find their way here too. You're also invited to leave a comment, letting us know what you enjoyed and how we could make this experience even better for you. For now, there's nothing you need to do. You don't need to remember anything or stay focused. Simply allow the words to pass by as you rest. Let's begin. Space is often described as empty, but this description is not quite accurate. What exists beyond Earth's atmosphere is better understood as a near-perfect vacuum, a state where matter is present in extraordinarily low concentrations. Even in the most advanced laboratories on Earth, where scientists work to remove as much air as possible from sealed chambers, it is impossible to create a vacuum as complete as what exists naturally in the depths of space. There will always be some residual gas molecules, some trace of matter remaining in any chamber built by human hands. The vacuum of space, by contrast, is far more profound. In outer space, particles do exist, but they are scattered so thinly that the average distance a single particle travels before encountering another is immense. This distance, far greater than anything achievable in terrestrial experiments, stretches across vast emptiness. The particles that do exist are primarily hydrogen plasma, the simplest and most abundant form of matter in the universe, along with electromagnetic radiation that passes silently through the void. The vacuum of space is not absolute emptiness, but rather a profound quietness of matter, a stillness that extends in all directions. When considering the most remote regions between galaxies, the density of matter becomes even more remarkable. In these intergalactic expanses, vast stretches of space where no stars shine nearby, there might be only 1 to 10 atoms in every cubic meter of space. To imagine this, picture a cube of space the size of a small room, and within that entire volume, perhaps only a handful of atoms drifting in isolation. This is a level of sparseness difficult to comprehend from the perspective of Earth, where matter surrounds us constantly, where every breath contains countless molecules. The atoms present in these remote regions are mainly ionized hydrogen and helium, forming what is called the intergalactic medium. Though nearly invisible and impossibly dilute, this medium exists across such vast volumes that it accounts for a significant portion of the ordinary matter in the universe. It is there, quietly filling the spaces between everything we can see. The observable universe contains structures at scales that extend beyond easy imagination. Current estimates suggest there are approximately 2 trillion galaxies within the portion of the universe we can observe, the part from which light has had time to reach us. Earlier calculations often cited hundreds of billions, a number already difficult to picture, but as instruments have improved and methods have been refined, the number has grown. These galaxies are the fundamental building blocks of the cosmic landscape, arranged in patterns of varying density throughout space. Each one is a system unto itself, separated from the others by distances that make interstellar space seem almost crowded by comparison. Each of these galaxies is itself a collection of enormous scale. A large galaxy, such as our own Milky Way or the neighboring Andromeda, typically contains between 100 billion and 400 billion stars. The exact number varies, and some galaxies contain even more. These stars vary widely in their properties. Some are small, dim red dwarfs that burn their fuel slowly and steadily over trillions of years, longer than the current age of the universe. Others are massive blue giants that shine intensely but briefly, living out their entire lives in just a few million years before ending in spectacular explosions. Many of these stars are accompanied by planetary systems, though most remain too distant to be studied in detail. We can infer their presence, but we cannot yet see them clearly. Beyond the stars themselves, galaxies contain substantial quantities of gas and dust spread throughout the space between stellar systems. This interstellar material is not merely leftover debris, not just the remnants of older stars. It represents the raw ingredients from which future generations of stars will form, the matter that will one day collapse and ignite. All of this matter, both luminous and dark, is held together by the collective gravitational influence of the galaxy itself, forming a discrete system within the larger universe. Each galaxy is a gravitationally bound island, maintaining its structure even as the space between galaxies continues to expand. The distances between major galaxies are measured in millions of light-years. Andromeda, the nearest large galaxy to the Milky Way, lies approximately 2.5 million light-years away. At these scales, the expansion of the universe becomes relevant. Most galaxies that are not bound together by mutual gravity are gradually moving apart, not because they are traveling through space in the conventional sense, but because the space between them is itself expanding. This expansion is gentle but persistent, occurring everywhere at once. Direct collisions or interactions between galaxies unfold over timescales of billions of years, slow enough that if observed over a human lifetime, they would appear almost entirely still. Galaxies are gravitationally bound systems, meaning their internal components are held together despite the expansion occurring on larger scales. Within each galaxy, there is ordinary matter that we can see and measure directly, including stars, gas, and dust. But there is also another component, one that does not emit light or interact with electromagnetic radiation in any detectable way. This is dark matter, and it provides the additional gravitational influence necessary to explain how galaxies rotate and hold their shapes. Without dark matter, the observed motions of stars within galaxies would not be possible based on visible matter alone. Stars at the outer edges of galaxies move faster than they should, given the amount of visible mass. Something unseen is holding them in place. On the very largest scales, when the universe is considered as a whole, a principle emerges. This is called the cosmological principle, and it states that the universe is both homogeneous and isotropic. Homogeneity means that when averaged over sufficiently large distances, far larger than individual galaxies or even galaxy clusters, the density of matter is roughly uniform throughout space. Isotropy means that the universe looks essentially the same in every direction. If you could step outside the universe and look at it from any angle, it would appear similar. When scales larger than 300 million light-years are considered, local variation smooth out and a general uniformity becomes apparent. The universe, at its largest scales, has no preferred direction or location. Galaxies do not exist in isolation. They gather into clusters, which represent some of the most massive gravitationally bound structures known. A galaxy cluster might contain hundreds or even thousands of individual galaxies, all moving within a shared gravitational potential, all held together by their mutual attraction. Between these galaxies, there is hot gas that emits X-rays, known as the intracluster medium. This gas is heated to millions of degrees by the gravitational energy of the cluster. Surrounding and permeating everything is a massive halo of dark matter, which provides the gravitational framework that holds the cluster together. The gravitational influence of such a cluster is strong enough to bend the path of light from objects even farther away, a phenomenon called gravitational lensing. Light from distant galaxies is curved as it passes through the cluster's gravitational field, sometimes creating multiple images or arcs of the same distant object. Beyond clusters, there are superclusters, which are collections of multiple galaxy clusters and groups. Superclusters represent some of the largest known structures in the cosmos, often spanning hundreds of millions of light-years and containing tens of thousands of galaxies. Unlike clusters, superclusters are not always gravitationally bound as single units. Some may be expanding along with the rest of the universe, their components gradually drifting apart over time. They serve as nodes within a larger framework, contributing to the overall architecture of space. They are waypoints in the cosmic landscape. This larger architecture is known as the cosmic web. When the distribution of galaxies is mapped across enormous distances using data from millions of galaxies, a pattern emerges. Galaxies are not scattered randomly, like grains of sand on a beach. Instead, they form long, thin filaments that stretch across hundreds of millions of light-years. These filaments interconnect at dense nodes, which are the galaxy clusters and superclusters. The filaments act as conduits, channeling gas and matter into galaxies and clusters, feeding the ongoing process of star formation. This web-like structure is the result of small fluctuations in the density of matter in the early universe, fluctuations that were amplified over billions of years by gravity. What began as tiny variations in an otherwise smooth distribution has grown into the grand structure we observe today. Between the filaments of this cosmic web are regions called voids. These are vast, roughly spherical expanses where very few galaxies exist and the density of matter is significantly lower than elsewhere. Voids are not completely empty, but they represent the least dense environments in the known universe. They occupy the majority of the universe's total volume, with diameters that can reach anywhere from 30 million to 500 million light-years. To cross a void at the speed of light would take tens of millions of years. The existence of voids emphasizes that matter in the universe is not evenly distributed at every scale, but rather organized into a delicate, interconnected structure of fullness and emptiness. The universe has texture. The Milky Way, our own galaxy, is classified as a barred spiral galaxy. This designation indicates a specific structure, one in which a central bar-shaped formation of stars extends across the core, with spiral arms curving outward from the end of this bar. The Solar System, which includes the Sun and all the planets that orbit it, resides within this galactic structure. We are part of this vast rotating disk of stars. This places the Milky Way among the majority of large galaxies in the nearby universe that exhibit a disk-like shape and distinct patterns of rotation. The spiral arms are regions where stars and gas are concentrated, creating the characteristic pinwheel appearance that can be seen in other galaxies similar to our own. The Sun itself is a G-type main sequence star, positioned within a region called the Orion Arm, also known as the Orion Spur. This is a minor spiral arm of the Milky Way, not one of the major structures but a smaller feature branching off from them, like a tributary branching from a river. The Sun is located approximately 26,000 light-years from the galactic center, a distance that places it roughly halfway between the center and the outer edge of the disk. This is a relatively low-density region of the stellar disk, not crowded with neighboring stars. This position allows for stable orbital dynamics, which have been maintained over billions of years, contributing to the long-term stability of the planetary system. The relative isolation has been, in many ways, beneficial. The Solar System follows a nearly circular orbit around the galactic center, a region marked by a high concentration of stars and the presence of a supermassive black hole known as Sagittarius A. The Sun and its planets travel at an average velocity of approximately 230 km per second relative to this center. This is a substantial speed, though it occurs so smoothly that we feel no sensation of this motion. It takes roughly 225 to 250 million years to complete one full revolution around the galaxy. This duration is sometimes referred to as a galactic year, though it is far longer than any human timescale, longer than the existence of dinosaurs, longer than complex life has existed on Earth. The stellar disk of the Milky Way is a flattened, rotating region that contains the majority of the galaxy's stars and the gas and dust that fills the space between them. Measurements indicate that the disk spans approximately 100,000 to 150,000 light-years in diameter, an expanse so vast that light itself takes that long to cross from one edge to the other. Recent observations suggest that stellar populations may extend even farther, beyond these traditional boundaries. While the disk is vast in its breadth, it is relatively thin, averaging only about 1,000 light-years in height across most regions. If the galaxy were scaled down to the size of a coin, it would be thinner than a sheet of paper. Light moves through the vacuum of space at a fundamental constant, exactly 299,792,458 meters per second. This number is precise, unchanging. This speed represents the upper limit for the transfer of all energy, matter, and information in the universe. Nothing can move faster than this. Because this velocity is unchanging, regardless of who measures it or how they are moving, it serves as the foundation for defining astronomical distances and for understanding the relationship between time and spatial separation in the framework of relativity. The speed of light is woven into the very structure of space-time. A light-year is a unit of length used to express the vast distances between stars and galaxies. It is defined as the distance that light travels in a vacuum over the course of 1 Julian year, which is 365¼ days. This unit becomes essential when measuring the gaps between celestial objects, where conventional units like kilometers or miles become impractical and difficult to comprehend. The numbers become unwieldy, too large to hold in the mind. By using the speed of light as a standard, astronomers can express distances in a way that remains consistent across the immense scales of space. It also naturally connects distance with time, a reminder that to look far away is also to look far back. The numerical value of 1 light-year is approximately 9.46 trillion kilometers, or 5.88 trillion miles. These are numbers that resist intuitive understanding. To provide some perspective, the distance from the Earth to the Sun is only about 8 light minutes. Light leaves the Sun, travels through empty space, and arrives at Earth roughly 8 minutes later. The scale of a light-year illustrates the extreme isolation of stellar systems. Even traveling at the speed of light, which nothing with mass can achieve, it would take over 4 years to reach the nearest star, and nearly a decade to complete a round trip to the nearest neighboring star system. At speeds achievable by current spacecraft, the journey would take tens of thousands of years. A parsec is another unit of distance, derived from the method used to measure the distance to nearby stars through trigonometric parallax. This technique involves observing how a nearby star appears to shift position against the background of more distant stars as Earth moves along its orbit. 1 parsec is defined as the distance at which one astronomical unit, the distance between Earth and the Sun, subtends an angle of 1 arcsecond. An arcsecond is an incredibly small angle, 1/3600th of a degree. This unit is preferred by professional astronomers because it relates directly to the observational data collected through telescopes. The relationship between these two units establishes that 1 parsec is equivalent to approximately 3.26 light-years. While light-years are often used in general communication to emphasize the time light takes to travel, parsecs are the standard for mapping coordinates within the galaxy and calculating the properties of celestial objects. Proxima Centauri is a small, low-mass red dwarf star and the closest known stellar neighbor to the Sun. It is located at a distance of approximately 4.24 light-years. Despite this relative proximity, despite being the nearest star beyond our own, Proxima Centauri is not visible to the naked eye from Earth due to its low luminosity. It shines too dimly to be seen without instruments. It is part of the Alpha Centauri triple star system, a collection of 3 stars bound together by gravity. The distance to Proxima Centauri serves as a useful reference point for understanding the typical spacing between stars within the spiral arms of the Milky Way. Stars are, on average, several light-years apart. Because the speed of light is finite, because it takes time for light to traverse space, the observation of distant celestial objects is inherently a look back in time. The light currently reaching a telescope left its source at a point in the past, and the delay is proportional to the distance. An object located 100 light-years away is observed as it existed a century ago. We see it not as it is now, but as it was then. This natural delay allows astronomers to study the history of the universe simply by observing objects at varying distances. The deeper we look into space, the further back we look in time. Light from the most distant observable galaxies has traveled for over 13 billion years before reaching instruments on Earth. These photons have been journeying through expanding space for nearly the entire age of the universe. Telescopes such as the Hubble Space Telescope and the James Webb Space Telescope act as chronological probes, capturing photons that were emitted when the universe was in its infancy, when the first galaxies were just beginning to form. These observations are critical for understanding the formation of the first stars and the subsequent assembly of large-scale structures across cosmic time. They allow us to witness the universe growing up. The darkness of the night sky is a phenomenon that once posed a puzzle. If the universe were infinite in age and unchanging, if it had always existed in a static state, then every line of sight would eventually terminate at the surface of a star, and the sky would be as bright as the sun itself. The entire night sky would glow. However, the universe is approximately 13.8 billion years old, and it is expanding. Light from the most distant regions has not yet had time to reach us. Those regions are simply too far away. Additionally, the expansion of space causes light to shift into wavelengths that are no longer visible to our eyes. This explains why the night remains dark, why the sky between the stars is black. When light from distant galaxies is analyzed, when it is spread out into a spectrum showing all its component wavelengths, the wavelengths of its spectral lines are found to be shifted toward the longer, redder end of the spectrum compared to the same lines measured in a laboratory. This phenomenon is known as cosmological redshift. It occurs because the photons are stretched as they travel through expanding space. The degree of redshift is directly proportional to the distance of the galaxy. The farther away a galaxy is, the more its light is shifted. This relationship has become fundamental to measuring the scale of the universe. This redshift is interpreted primarily as a result of the expansion of space itself, rather than galaxies moving through space like objects in motion through a stationary medium. As the fabric of spacetime expands, the wavelength of light propagating through it is elongated, stretched along with the space it travels through. This observation provides the empirical basis for the understanding that the universe was once in a much denser and hotter state, compressed into a much smaller volume, and has been expanding for approximately 13.8 billion years. The universe has been growing larger and cooler for all this time. Gravity is one of the four fundamental forces of nature. It is characterized by the mutual attraction between all entities that possess mass or energy. Everything that has mass pulls on everything else, no matter how distant. Unlike the strong or weak nuclear forces, which operate only at subatomic scales, confined to the interior of atomic nuclei, gravity has an infinite range. Its influence extends without limit, though it weakens with distance. While it is the weakest of the fundamental interactions at the level of individual particles, far weaker than electromagnetism or the nuclear forces, its cumulative nature makes it the dominant force across astronomical distances. Gravity governs the orbits of planets, the life cycle of stars, and the motion of entire galaxies. At the largest scales, it is gravity that shapes the universe. In the framework of general relativity, gravity is not described as a traditional force, not as an invisible pull between objects. Instead, it is understood as a geometric property of space-time. Mass and energy cause the four-dimensional fabric of the universe, comprising three spatial dimensions and one dimension of time, to curve. A common analogy involves imagining a heavy sphere placed on a flexible sheet. The resulting depression, the dip created in the fabric, dictates the movement of smaller objects nearby. They roll toward the depression not because they are being pulled, but because the geometry of the surface has changed. Thus, matter tells spacetime how to curve, and spacetime tells matter how to move. This is the essence of general relativity. Within this curved spacetime, objects in freefall do not travel in straight lines as defined by Euclidean geometry, the flat geometry taught in schools. Instead, they follow what are called geodesics. A geodesic represents the shortest possible path between 2 points in a curved manifold, the straightest path available in a curved space. In the absence of non-gravitational forces, such as friction or electromagnetic thrust, a planet orbiting a star or a photon passing near a massive galaxy is simply following the natural curvature of the local geometry along a geodesic path. From the object's own perspective, it is moving in a straight line. It is the space around it that is curved. Gravitational interaction is notable for its long-range reach and its inability to be shielded or blocked. Unlike electromagnetic forces, which can be neutralized by shielding materials or by balancing positive and negative charges, gravity is always attractive and possesses no negative equivalent. There is no such thing as negative mass, no way to create antigravity. Any mass added to a system increases the total gravitational field, and no known material can prevent a gravitational field from penetrating it. Its influence is felt throughout the vacuum of space, regardless of what lies in between, regardless of intervening matter. Gravity cannot be turned off or redirected. According to Newton's law of universal gravitation, the force of attraction between two masses is inversely proportional to the square of the distance between them. This inverse square law implies that if the distance between two celestial bodies is doubled, the gravitational pull between them is reduced to 1/4 of its original strength. If the distance is tripled, the force drops to 1/9. While general relativity provides a more comprehensive description for extreme conditions involving very large masses or high speeds, the Newtonian model remains highly accurate for calculating orbits and trajectories within most of the solar system. For everyday astronomical calculations, Newton's equations work perfectly well. General relativity also predicts that the passage of time is influenced by the proximity of mass. In regions of stronger gravitational potential, closer to a massive body like a planet or a black hole, clocks tick more slowly relative to clocks located in weaker gravitational fields. This is not an illusion or a mechanical defect. Time itself passes at different rates depending on the strength of the gravitational field. This effect is measurable and must be accounted for in practical applications. Atomic clocks on satellites in Earth's orbit must be corrected for the fact that they run slightly faster than clocks on the planet's surface. Without these corrections, systems like GPS would quickly accumulate errors. Time is also affected by relative velocity. According to the principles of special relativity, as an object's speed increases relative to a stationary observer, time for that moving object appears to slow down from the observer's perspective. The faster an object moves, the more pronounced this effect becomes. This effect becomes significant only at speeds that are substantial fractions of the speed of light, what physicists call relativistic speeds. Experimental evidence for this has been found in the behavior of high-speed subatomic particles, which exhibit longer lifespans when moving at such velocities. Particles that would normally decay in microseconds can survive for much longer when traveling close to the speed of light. Time dilation resulting from constant velocity is central to special relativity, which deals with observers in constant motion, moving in straight lines at unchanging speeds. It arises because the speed of light must remain constant for all observers, regardless of their motion. For the speed of light to be the same whether you are moving toward a light source or away from it, whether you are standing still or racing through space, the interval of time itself must adjust. This leads to the conclusion that simultaneity is not absolute but depends on the relative motion of the observers involved. Events that appear simultaneous to one observer may not appear simultaneous to another observer moving at a different velocity. Gravitational time dilation is a related but distinct consequence of general relativity. It is rooted in the equivalence principle, which states that the effects of gravity are locally indistinguishable from the effects of acceleration. If you were in a sealed room, you could not tell the difference between the room sitting on the surface of a planet or the room being accelerated through space. Because acceleration and gravity are equivalent in their effects, and acceleration affects the geometry of space-time, gravity must also alter the rate at which time passes. The two are fundamentally linked. A fundamental postulate of relativity is that the speed of light in a vacuum is invariant, unchanging under all circumstances. Regardless of whether an observer is stationary or moving at high velocity toward or away from a light source, the measured speed of the incoming photons remains exactly the same. This is deeply counterintuitive. In everyday experience, velocities add and subtract. If you run toward someone throwing a ball, the ball appears to approach you faster. But light does not behave this way. Its speed is always measured as the same constant. This constancy defies classical intuition and necessitates the relativistic warping of space and time to preserve this universal limit. The universe adjusts space and time to keep the speed of light constant. As an object with mass approaches the speed of light, its momentum and energy increase toward infinity. The closer it gets to the speed of light, the more energy is required to accelerate it further. Accelerating a mass to exactly the speed of light would require an infinite amount of energy, which is physically impossible. Therefore, the speed of light serves as an absolute cosmic speed limit for any object with mass. Only massless particles, such as photons, can travel at this speed, and they must always travel at this speed in a vacuum. They can never be at rest. For them, there is only motion at the speed of light. Electromagnetic radiation is characterized by a dual nature. It exhibits properties of both a continuous wave and discrete packets of energy known as photons. As a wave, it consists of oscillating electric and magnetic fields that propagate perpendicular to one another, undulating through space. As a particle, the photon acts as the elementary quantum of light, carrying a specific amount of energy determined by its frequency. This dual nature is fundamental to quantum mechanics and explains how light interacts with matter, how it can behave like a wave in some experiments and like a particle in others. Photons are categorized as massless particles. Because they lack mass, they are not subject to the inertia that limits the speed of objects containing matter. This allows them to travel at the universal speed limit in a vacuum without requiring any energy to maintain that speed. Although they have no mass, photons carry momentum and energy, which allows them to exert pressure on physical surfaces. This phenomenon has been considered for theoretical propulsion systems, where spacecraft could be pushed forward by reflecting photons from a large sail. The electromagnetic spectrum encompasses the entire range of frequencies and wavelengths of electromagnetic radiation. This spectrum is continuous, with no gaps, extending from extremely long wavelength radio waves to incredibly short wavelength gamma rays. In a vacuum, all these forms of radiation travel at the same constant speed, the speed of light, but they interact with matter differently depending on their energy levels. This determines their usefulness in astronomical observation and communication. Different wavelengths reveal different phenomena, different aspects of the universe. Visible light represents a very narrow band of the electromagnetic spectrum, typically ranging in wavelength from approximately 380 to 750 nanometers. This is the only portion of electromagnetic radiation that the human eye has evolved to detect, a tiny sliver of the full spectrum. Different wavelengths within this band are perceived as different colors by our brains. Violet has the shortest wavelength and highest frequency, while red has the longest wavelength and lowest frequency. The rainbow of colors we see represents only a small window into the full range of light. X-rays and gamma rays occupy the highest frequency end of the spectrum and possess the highest energy per photon. Each individual photon carries a substantial amount of energy. These forms of radiation are produced by high-energy cosmic events, processes that involve extreme temperatures or violent motion. Such events include supernova explosions, where entire stars are torn apart, matter falling into black holes and being heated to millions of degrees, or the decay of radioactive nuclei. Because of their high energy, they can remove electrons from atoms, a process called ionization. This property requires specialized orbital telescopes for detection, since the Earth's atmosphere absorbs most of these rays before they can reach the ground. The atmosphere shields us from this high-energy radiation, making ground-based observation of these wavelengths impossible. Radio waves are located at the opposite end of the spectrum. They are characterized by the lowest frequencies and the longest wavelengths, which can range from millimeters to hundreds of kilometers. Some radio waves are longer than entire buildings. In an astronomical context, radio waves are emitted by a variety of sources scattered throughout the cosmos. These include pulsars, the rapidly spinning remnants of dead stars, cold interstellar gas clouds drifting between the stars, and the afterglow of the Big Bang itself. Unlike higher-frequency radiation, radio waves can pass through large clouds of interstellar dust without being absorbed or scattered. This allows astronomers to map regions of the galaxy that are obscured in visible light, to see through the dust to what lies beyond. The energy of a single photon is directly proportional to its frequency. The higher the frequency, the more energy the photon carries. This means that as the frequency of the radiation increases, moving up the spectrum from radio toward gamma rays, the energy carried by each photon also increases. High-frequency radiation like ultraviolet or X-rays is more energetic per photon and potentially more damaging to biological tissues and electronic components than low-frequency radiation like infrared or radio waves. This is why prolonged exposure to ultraviolet light from the sun can damage skin, while radio waves pass through our bodies without effect. A fundamental inverse relationship exists between the wavelength and frequency of light. These two properties are connected by the speed of light. Since the speed of light is constant in a vacuum, always the same value, an increase in frequency must result in a proportional decrease in wavelength. They move in opposite directions. Radiation with a high frequency therefore has a very short distance between successive wave crests, the peaks of the wave tightly packed together. In contrast, low-frequency radiation has long distances between crests, with the waves stretched out over great lengths. This relationship means that knowing one property allows you to calculate the other. According to the laws of thermodynamics, all matter with a temperature above absolute zero emits electromagnetic radiation due to the thermal motion of its constituent particles. The atoms and molecules that make up an object are always jiggling, always vibrating, and this motion produces radiation. This is known as thermal radiation. The distribution of wavelengths emitted depends on the temperature of the object. Cooler objects emit primarily in the infrared and radio bands, radiation we cannot see with our eyes. Hotter objects, like stars, emit significant amounts of visible and ultraviolet light. The color of a star tells us something about its temperature. There is a relationship between the temperature of an object and the total energy it radiates. This relationship is steep, dramatic in its consequences. Even a small increase in temperature results in a large increase in the amount of energy radiated from the surface. For example, doubling the absolute temperature of a star would cause it to radiate 16 times more energy from its surface. Not twice as much, but 16 times as much. This explains why massive, hot stars are so much more luminous than cooler ones, why they shine so much more brightly despite being made of the same basic materials. In the vacuum of space, the transfer of thermal energy occurs almost exclusively through radiation. Other methods of heat transfer that we experience on Earth, such as conduction and convection, require a physical medium like a gas or liquid to transport heat through direct contact or bulk movement of the fluid. These processes are ineffective in a vacuum, where there is no medium to carry the heat. An object in space can only cool down by emitting photons, by radiating its heat away as infrared light, and can only heat up by absorbing radiation from external sources like the sun or other stars. There is no air to warm it, no contact with anything else. The temperature of an object in space is determined by the balance between the radiation it absorbs and the radiation it emits. If it absorbs more than it emits, it warms up. If it emits more than it absorbs, it cools down. In direct sunlight near Earth's orbit, an object can reach temperatures well above 100 degrees Celsius as it absorbs intense solar radiation, baking in the unfiltered light. If that same object is then moved into shadow, shielded from the sun by another body, it will rapidly radiate its stored thermal energy into space, potentially dropping to temperatures below -150 degrees Celsius. The swings can be extreme, and they can happen quickly. An isolated object located in the vast voids of intergalactic space, far from the influence of any stars, in regions where darkness is almost complete, will eventually reach thermal equilibrium with its surroundings. It will cool until it matches the temperature of the space around it. The primary source of ambient radiation in these regions is the cosmic microwave background, the faint afterglow of the Big Bang. Because this radiation has a temperature of approximately 2.7 kelvins, just a few degrees above the coldest possible temperature, an isolated object will eventually cool until its temperature is just a few degrees above absolute zero. It will become nearly as cold as anything in the universe can be. Absolute zero is defined as 0 Kelvin, or approximately -273 degrees Celsius. It is the theoretical lower limit of the thermodynamic temperature scale, the point at which you cannot extract any more heat. At this state, the thermal motion of particles ceases according to classical physics. Atoms stop jiggling. In quantum mechanics, particles at absolute zero still possess what is called zero-point energy, a residual energy that remains even at the lowest temperature. But they are in their lowest possible energy state, and it is impossible to extract further heat from them. They cannot be made any colder. The vacuum of space is permeated by the cosmic microwave background, a faint glow of electromagnetic radiation that fills the entire universe. This radiation exists everywhere, in every direction, though it is invisible to human eyes. It has a thermal spectrum with a temperature of approximately 2.725 kelvins. This is not metaphorical warmth, but an actual temperature. It represents the oldest light in the universe, dating back to about 380,000 years after the Big Bang. At that time, the universe had cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, a hot fog of particles. After this moment, photons could travel freely through space for the first time. The light we detect now has been traveling ever since. The cosmic microwave background is characterized by its extreme uniformity. It is observed with near-perfect consistency across the entire sky, no matter where we point our instruments. There are minute fluctuations in temperature, tiny variations on the order of 1 part in 100,000, barely detectable even with sensitive equipment. But the overall consistency in every direction provides strong evidence for the principle that the universe is homogeneous and isotropic on the largest scales. These tiny variations, small as they are profoundly important. They are the imprints of density fluctuations in the early universe that eventually grew under the influence of gravity to form galaxies and large-scale cosmic structures. They are the seeds from which everything we see emerged. Ordinary matter, also known as baryonic matter, the matter made of protons, neutrons, and electrons, constitutes only about 5% of the universe's total energy density. Most of the universe is not made of this familiar substance. The vast majority of ordinary matter consists of the simplest elements. Hydrogen accounts for approximately 75% of the elemental mass of the universe, while helium makes up nearly 25%. These two elements were primarily created during the first few minutes of the universe's existence, forged in the intense heat following the Big Bang. All other elements, everything from carbon to iron to gold, make up less than 2% of the observable matter. We are made of the rare stuff. Elements heavier than helium, such as carbon, oxygen, iron, and gold, are synthesized within stars. Throughout their lives, stars act as cosmic forges, fusing lighter nuclei into heavier ones within their high-pressure cores. Elements heavier than iron cannot be created through normal stellar fusion, as the process would consume energy rather than release it. These elements are typically produced during the extreme conditions of a core collapse supernova or the merger of neutron stars, violent events where rapid processes occur at unimaginable temperatures and densities. When these stars expire, when they explode or shed their outer layers, they disperse these enriched materials into the space between stars, providing the chemical building blocks for future generations of stars, planets, and potentially life. We are made of stardust, quite literally. Star formation begins within giant molecular clouds, which are cold, high-density regions of gas and dust. These clouds are vast, stretching across hundreds of light-years, and they are the coldest places in the galaxy. When a portion of such a cloud exceeds a critical mass, when enough material gathers together, it undergoes gravitational collapse. Gravity overcomes the internal pressure, and the cloud begins to fall in on itself. As the material falls inward, gravitational potential energy is converted into heat, warming the core. This forms a dense, hot core called a protostar, not yet a true star but the beginning of one. Once the core temperature reaches approximately 10 million kelvins, hydrogen fusion ignites. The outward thermal pressure from this fusion then balances the inward pull of gravity, and the star reaches a stable state. It has been born. The longest stage of a star's existence is the main sequence phase. During this time, which can last billions of years, it remains stable by fusing hydrogen nuclei into helium within its core. This process releases a large amount of energy in the form of photons and neutrinos, particles that stream outward from the core. The star glows steadily, maintaining its structure through a delicate balance between the inward crush of gravity and the outward push of radiation pressure. The duration of this phase depends on the star's mass. More massive stars burn through their fuel quickly, while smaller stars are more conservative. The Sun, for example, is approximately halfway through its 10 billion-year main sequence lifetime. It has been shining steadily for about 5 billion years and will continue for about 5 billion more before significant changes begin. The Sun is classified as a G-type main sequence star, often referred to as a yellow dwarf, though it appears white to our eyes when viewed from space. It has a mass that serves as the standard unit of measurement for comparing other stars and celestial objects. When astronomers speak of a star having 3 solar masses or half a solar mass, they are using our Sun as the reference point. This mass determines its gravitational influence over the solar system, holding the planets in their orbits. It also determines the Sun's internal temperature and the rate at which it consumes its nuclear fuel. Mass is destiny for a star. A star's energy is generated in its innermost region, the core, where temperatures and pressures are high enough to overcome the repulsion between atomic nuclei. Nuclei carry positive charges, and like charges repel each other. Only under extreme conditions can they be forced close enough for the strong nuclear force to bind them together. This energy travels outward through different layers, moving first through zones where radiation dominates, then through zones where convection carries the heat, before being emitted from the surface as electromagnetic radiation. This constant outflow of energy provides the pressure necessary to prevent the star from collapsing under its own weight. The star is held up by its own light. There is an inverse relationship between a star's mass and its total lifespan. Although high-mass stars have more hydrogen fuel to burn, they consume it at an exponentially faster rate due to the extreme pressures in their cores. The greater the mass, the hotter and denser the core becomes, and the faster fusion proceeds. A star with 10 times the mass of the Sun might remain in its stable phase for only 20 million years, a brief moment in cosmic time. In contrast, a low-mass red dwarf can continue fusing hydrogen for trillions of years, far exceeding the current age of the universe. The smallest stars will outlive everything, burning quietly long after larger stars have expired. Low to intermediate mass stars, including those similar to the Sun, eventually exhaust their core hydrogen. When the fuel runs out, the core contracts and heats up, while the outer layers expand dramatically. The star transitions into a red giant, swelling to many times its original size. After shedding their outer layers in a gentle wind, expelled over thousands of years, the remaining core collapses into a white dwarf. A white dwarf is an extremely dense stellar remnant about the size of Earth, roughly the diameter of our planet but containing perhaps half the mass of the Sun. It is supported against further collapse by a quantum mechanical pressure, electrons refusing to be compressed beyond a certain limit. It no longer undergoes fusion and will slowly cool over billions of years, gradually fading from view. High-mass stars encounter a more violent end. Once they begin synthesizing iron in their cores, a turning point is reached. Fusion no longer produces energy beyond this point. Iron is the most stable nucleus, and fusing it consumes energy rather than releasing it. The core can no longer support itself against gravity. In less than a second, in a catastrophic instant, the core collapses. The collapse is so rapid that the outer layers fall inward before they realize the core is gone. They then rebound in a supernova explosion, one of the most energetic events in the universe. This event releases more energy than an entire galaxy of stars, briefly outshining the combined light of billions of ordinary stars. What remains behind depends on the mass of the core. If the core is less than about 3 solar masses, it leaves a neutron star. If more massive, it leaves a black hole. Neutron stars represent one of the few forms of stable matter at nuclear densities. Formed during the core collapse of a massive star, the remaining core is crushed by gravity until protons and electrons merge into neutrons, packing matter as tightly as it can be packed outside a black hole. A neutron star typically contains about 1.4 to 2.1 times the mass of the Sun within a radius of only 10 to 12 kilometers. To imagine this, picture the mass of the Sun compressed into a sphere no larger than a city. The resulting density is so extreme that a single teaspoon of neutron star material would have a mass of approximately 1 billion tons. These objects are often characterized by rapid rotation, spinning many times per second, an intense magnetic field stronger than anything we can create on Earth. Black holes are regions where the concentration of mass is so great that the curvature of spacetime becomes infinite at a central point. The gravitational pull in these regions is so intense that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. Because no information or radiation can exit a black hole, they cannot be observed directly through light. We cannot see them glowing or reflecting starlight. Instead, their presence is inferred by their gravitational influence on nearby stars and gas, by the way matter moves in their vicinity, orbiting something invisible. The event horizon serves as the boundary of a black hole. It is defined as the point of no return, where the gravitational pull is so steep that all possible paths for matter and light lead inward, toward the singularity at the center. There is no trajectory that leads back out. To an outside observer watching something fall toward a black hole, that object would appear to slow down and fade away as it approaches the event horizon, never quite appearing to cross it. Time dilation becomes extreme near the horizon. The object itself, however, experiences something different. In its own experience of time, it passes through the boundary and continues inward without noticing anything particularly special at the moment of crossing, though what awaits inside remains beyond our full understanding. Supermassive black holes are distinct from those formed by collapsing stars. They possess masses ranging from millions to billions of times that of the Sun, far more massive than any single star could produce through collapse. Evidence suggests that nearly every large galaxy contains such an object at its gravitational center, lurking in the core. In the Milky Way, this object is Sagittarius A, which has a mass of approximately 4 million times that of the Sun. Despite this enormous mass, it remains relatively quiet, not actively consuming large amounts of matter at present. The origin of these massive objects is a subject of ongoing research, as they appear to have grown alongside their host galaxies since the early stages of the universe, their histories intertwined. When matter falls toward a compact object like a neutron star or black hole, it rarely falls directly in. Instead, because of conservation of angular momentum, it forms a rotating structure called an accretion disk. The material spirals inward slowly, orbiting faster and faster as it gets closer. Gravitational energy is converted into thermal energy through friction and turbulence within the disk. As the material spirals inward and accelerates, heating through compression and collision, it reaches temperatures of millions of degrees. At these temperatures, it emits high-energy radiation in the form of X-rays and ultraviolet light, glowing intensely despite being so close to an object from which nothing can escape. In some cases, particularly around supermassive black holes, this process powers active galactic nuclei, which can outshine the entire host galaxy. The black hole itself remains dark, but the matter falling toward it creates a brilliant beacon. The interstellar medium is the matter and radiation that exists in the space between star systems within a galaxy. It is not a uniform vacuum, not simply empty space. Rather, it is a complex environment consisting of gas, dust, and cosmic rays, a tenuous but pervasive presence. It is essential to the galactic ecosystem, as it provides the reservoir of material for new star formation and receives the heavy elements and energy from dying stars. It is constantly cycling, material moving from clouds to stars and back to clouds again. It exists in various phases, ranging from cold, dense molecular clouds to hot, ionized gas that has been heated to millions of degrees. Interstellar gas constitutes the majority of the mass of the interstellar medium, with hydrogen being the most abundant component, as it is everywhere in the universe. This gas exists in different states, depending on local conditions. There is neutral atomic hydrogen, individual atoms drifting through space, which is widely distributed throughout the galaxy. There is molecular hydrogen, where atoms pair up to form molecules, found in cold, dense clouds where conditions allow molecules to survive. And there is ionized hydrogen, where electrons have been stripped away, which is often found near hot, young stars that emit intense ultraviolet radiation. The transition between these states is governed by the local temperature, density, and the intensity of the surrounding radiation field. Each region has its own character. Molecular clouds are the densest and coldest parts of the interstellar medium. Temperatures in these regions often fall as low as 10 to 20 kelvins, cold enough that most atoms bond into molecules. In these clouds, hydrogen atoms pair up to form molecules, the simplest molecular form. Because the clouds are dense enough to shield their interiors from ultraviolet radiation, blocking the light that would break molecules apart, they allow for the gravitational instabilities that lead to star formation. Shielded from disruption, gravity can gather material together. These stellar nurseries can span hundreds of light-years and contain enough mass to produce thousands of stars, entire generations born from a single cloud. Interstellar dust consists of microscopic solid particles composed primarily of silicates, carbon compounds, and ice. These are tiny grains, each one smaller than particles of smoke. Although dust makes up only about 1% of the mass of the interstellar medium, far less than the gas, it has a significant effect on observations. Dust grains absorb and scatter shorter wavelengths of light more effectively than longer wavelengths. Blue light, with its shorter wavelength, is scattered and absorbed more readily than red light. This results in what astronomers call extinction, where distant objects appear dimmer than they would otherwise, as if viewed through a haze. It also causes reddening, where objects appear redder than their true color. This is similar to the effect of Earth's atmosphere on a setting sun, which appears orange or red because blue light has been scattered away. The same principle operates in space, but over vastly greater distances. Nebulae are localized concentrations of interstellar gas and dust that become visible either because they emit light, reflect light from nearby stars, or obscure light from behind them. They are islands of visibility in the darkness. Emission nebulae are often colored red by the ionization of hydrogen, where energetic photons strip electrons from hydrogen atoms, and when those electrons recombine, they emit red light. These are regions of active star formation, glowing with the birth of new stars. Reflection nebulae appear blue because the dust particles scatter starlight, and blue light scatters more effectively, the same reason Earth's sky is blue. Dark nebulae are so dense that they block visible light entirely, appearing as voids against the background of the Milky Way, silhouettes against the stars. They are not truly empty but rather opaque, hiding what lies beyond. A planetary nebula is an emission nebula consisting of an expanding, glowing shell of ionized gas ejected from red giant stars late in their lives. Despite the name, which can be misleading, they have no connection to planets. The term originated from their circular, planet-like appearance in early telescopes, when resolution was limited and they appeared as round disks. As the star sheds its outer layers, expelled in a gentle wind over thousands of years, the exposed hot core, a budding white dwarf at the center, emits ultraviolet radiation. This radiation ionizes the ejected gas, causing it to glow with distinct colors, creating structures of remarkable beauty. These nebulae shine for several tens of thousands of years before they dissipate, fading back into the interstellar medium. Supernova remnants are the structural remains of a stellar explosion. When a supernova occurs, when a massive star reaches the end of its life and explodes, it ejects the star's outer layers at velocities approaching 10% the speed of light. This material rushes outward at extraordinary speeds. This ejector creates a powerful shock wave that plows into the surrounding interstellar medium, pushing through the existing gas like a cosmic bulldozer. The collision heats the gas to millions of degrees and accelerates particles to high energies. These remnants are crucial for distributing heavy elements like iron and nickel into space, enriching the galaxy with the products of stellar nucleosynthesis. They can also trigger the collapse of nearby molecular clouds through the pressure of their expanding shells, beginning a new cycle of star formation. Death gives rise to birth. Cosmic rays are subatomic particles, primarily protons, and atomic nuclei, stripped of their electrons and accelerated to velocities approaching the speed of light. These are not rays in the traditional sense but rather particles traveling at relativistic speeds. They originate from high-energy environments within and beyond our galaxy, such as the shock waves of supernova remnants and the active cores of distant galaxies, places where extreme conditions exist. Upon entering the region of space surrounding the Sun or a planetary atmosphere, cosmic rays represent a significant source of ionizing radiation, capable of impacting electronic systems and biological tissues, though they are largely invisible to our senses. Magnetic fields are pervasive throughout the cosmos, existing at planetary, stellar, and galactic scales. They thread through space like invisible filaments. Because cosmic rays and solar wind particles carry an electric charge, they are subject to forces exerted by these magnetic fields. Rather than traveling in straight lines across space, charged particles spiral along magnetic field lines, their paths bent and twisted. This interaction means that the paths of these particles are often highly convoluted, making it difficult to trace them back to their original point of origin in the distant universe. They arrive from seemingly random directions, their histories obscured by their winding journeys. The solar wind is a continuous outflow of plasma consisting mainly of electrons, protons, and alpha particles originating from the Sun's corona, the outermost layer of the Sun's atmosphere. Driven by the extreme temperature of the corona, which reaches millions of degrees, this plasma overcomes the Sun's gravity and expands into the solar system at speeds ranging from 300 to 800 kilometers per second. This is not a gentle breeze but a continuous stream flowing outward in all directions. This wind is not uniform across time or space. Its density and velocity vary according to the Sun's magnetic activity and the 11-year solar cycle, periods when the Sun is more or less active, producing more or fewer eruptions and disturbances. The heliosphere is a vast, bubble-like region of space dominated by the Sun's magnetic influence and the solar wind. It extends far beyond the orbit of the planets, reaching into the space between stars. It acts as a protective shield for the solar system, significantly reducing the influx of high-energy interstellar cosmic rays that would otherwise flood the inner planets. The boundary where the solar wind's pressure is balanced by the pressure of the interstellar medium is known as the heliopause. This marks the transition from the solar environment to truly interstellar space, the point where the Sun's influence fades and the galaxy takes over. A few spacecraft have crossed this boundary, venturing into the space beyond. Interplanetary space is filled with what is called the interplanetary medium, a sparse collection of gas, plasma, and microscopic dust particles. This medium is permeated by the extension of the Sun's own magnetic field, carried outward by the solar wind like a spiral pattern frozen into the flow. This environment is highly dynamic, constantly changing. Solar flares and coronal mass ejections periodically inject massive amounts of energy and matter into the interplanetary system, sending bursts of particles racing outward toward the planets. These events can create disturbances that ripple through the solar system. Planetary magnetic fields create regions of space known as magnetospheres, which act as buffers against the incoming solar wind. These are protective bubbles surrounding planets that possess magnetic fields. When the solar wind encounters a magnetosphere, it is largely deflected around the planet, flowing past like water around a rock in a stream. Some particles can become trapped in radiation belts or funnel toward the poles, following magnetic field lines down toward the surface. In the case of Earth, this interaction generates the aurorae, the northern and southern lights, and prevents the solar wind from directly stripping away the upper atmosphere over geological timescales. Without this protection, Earth's atmosphere might have been gradually eroded away. The orbits of planets are the result of a balance between the planet's forward velocity and the gravitational pull of its parent star. A planet moves forward through space while simultaneously falling toward the star, and these two motions combine to create a stable orbit. According to the laws of planetary motion, these orbits are generally elliptical rather than perfectly circular, though many are close to circular. As a planet moves along its orbit, it is effectively in a continuous state of free fall toward the star, but its sideways motion is sufficient to ensure it continually misses the star's surface. The planet is falling and missing, over and over. The Moon is held in its orbit by the mutual gravitational attraction between its mass and the mass of the Earth. While the Earth's gravity pulls the Moon inward, the Moon's tangential velocity, its motion sideways through space, provides the outward motion needed to maintain its orbital distance. Both bodies technically orbit a common center of mass, a point somewhere between them, though that point lies deep within the Earth's interior because Earth is so much more massive. The Moon does not orbit the exact center of the Earth, and the Earth wobbles slightly as the Moon moves around it. Tidal forces occur because gravity is not uniform across an extended object. Gravity is stronger on the side of an object closest to a mass than on the far side, creating a gradient of gravitational pull. On an extended body like the Earth, the Moon's gravity pulls more strongly on the near-side oceans than on the planet's center, and more strongly on the center than on the far-side oceans. This difference in force stretches the body along the axis pointing toward the gravitational source, elongating it slightly. This leads to phenomena such as ocean tides, the rising and falling of sea levels, and the internal heating of moons through tidal friction. Jupiter's moon Io, for example, is heated internally by the constant flexing caused by tidal forces, making it the most volcanically active body in the solar system. The principles of classical mechanics apply uniformly to objects both on the Earth's surface and in deep space. The same rules govern a falling apple and a satellite in orbit, a thrown ball and a planet circling the Sun. Whether it is a familiar object in our everyday experience or a distant celestial body, the motion is dictated by the relationship between force, mass, and acceleration. This is the foundation laid by Newton centuries ago. This universality of physical laws allows scientists to use terrestrial data and mathematical models to predict the movement of celestial bodies with precision. What works here works everywhere. The equations do not change. In a stable circular orbit, the force required to keep an object moving in a circle is provided entirely by gravity. The inward pull of gravity supplies exactly the right amount of force to curve the object's path into a circle. For an object to remain in a stable orbit closer to a massive body, it must travel at a higher velocity than an object in a more distant orbit. This is because the gravitational pull is stronger at smaller distances, requiring a greater speed to maintain balance to prevent the object from spiraling inward. A satellite in low Earth orbit must travel at approximately 7.8 kilometers per second, racing around the planet once every 90 minutes or so. A satellite in a much higher orbit travels at only about 3.1 kilometers per second, moving more slowly through its larger orbit. Escape velocity represents the minimum speed an object must reach to break free from the gravitational field of a massive body without any further acceleration, without any additional push. Once this speed is achieved, the object can coast away indefinitely. This velocity is determined by the mass of the body and the distance from its center. For Earth, the escape velocity at the surface is approximately 11.2 kilometers per second. Once an object reaches this speed, its kinetic energy, the energy of its motion, is equal to its gravitational potential energy, the energy binding it to the planet. The two balance out, and the object can escape, drifting away into space without needing any further propulsion. Planetary systems originate from the gravitational collapse of massive molecular clouds. As a core within such a cloud collapses to form a protostar, the beginning of a new star, the surrounding material does not simply fall straight in. Instead, it forms a flattened, rotating structure known as a protoplanetary disk. This disk is where planets are born. Within this disk, solid grains, tiny particles of dust and ice, collide and adhere through accretion, sticking together when they touch. They gradually form larger bodies, growing from dust to pebbles to boulders to mountains. Over millions of years, these bodies gather enough mass to become planets, sweeping up most of the material in their orbital paths, clearing their neighborhoods. What begins as a cloud of dust ends as a system of worlds. The transition from a spherical cloud of gas and dust to a flattened disk is a direct consequence of the conservation of angular momentum. This is a fundamental principle of physics. As the initial cloud contracts under its own gravity, shrinking inward, any slight initial rotation, even a tiny spin, is amplified. As the cloud gets smaller, it spins faster, like a figure skater pulling in their arms. This increased rotation generates effects that resist collapse along the equator but not along the poles. The cloud flattens into a disk, thin and wide. This principle explains why planetary systems are not spherical collections of planets orbiting in random directions, but are instead organized along a central plane. The disk is the natural shape. Due to the flattening of the original protoplanetary disk, the orbits of the resulting planets are generally coplanar, meaning they lie within a few degrees of a common plane. In the solar system, this plane is known as the ecliptic plane, defined by Earth's orbit. If you could view the solar system from the side, you would see the planets arranged in a relatively flat configuration, not scattered in 3 dimensions. While gravitational interactions with other bodies can slightly incline a planet's orbit over time, nudging it a few degrees one way or another, the fundamental alignment remains. It is a signature of the system's birth from a single, unified rotating disk of material. In accordance with the dynamics of the early protoplanetary disk, nearly all major bodies in the solar system exhibit what is called prograde motion, meaning they orbit the Sun in the same direction that the Sun itself rotates. Everything spins the same way. This shared directionality is a result of the collective motion of the original solar nebula, the cloud from which everything formed. While most planets also rotate on their axes in this same direction, spinning the same way they orbit, some exceptions exist. Venus rotates backward, and Uranus is tilted on its side. These anomalies are likely due to major collisions or tidal interactions occurring later in the system's history, events that altered their spins. Moons, or natural satellites, are celestial bodies that are gravitationally bound to planets, dwarf planets, or even large asteroids. They are companions, orbiting their parent bodies. They can form in different ways. Some formed concurrently with their parent planet from a subdisk of material, a smaller disk within the larger protoplanetary disk. Others were captured by the planet's gravity from a passing orbit, wandering bodies that came too close and were caught. Still others result from massive impacts that eject planetary crust into orbit, where it later coalesces into a moon. Our own moon is thought to have formed this way, from debris thrown into space by a collision early in Earth's history. Moons vary widely in composition and geological activity, ranging from frozen, cratered surfaces that have remained unchanged for billions of years to worlds with subsurface oceans or active volcanic plumes. Planetary ring systems, most prominent around Saturn but also present around Jupiter, Uranus, and Neptune, are composed of vast numbers of individual particles. These are not solid structures but collections of countless separate objects. These particles range in size from microscopic dust grains to boulders several meters in diameter, and they are primarily composed of water, ice, and rocky material. These rings are maintained by gravitational resonances, where the orbital periods of particles align with the periods of nearby moons, and by the influence of shepherd moons, small moons that orbit near the rings and help keep the particles confined. The rings are often located within what is called the Roche limit, a distance from the planet where tidal forces are so strong they prevent the particles from accreting into a single moon. If they tried to gather together, they would be pulled apart. Asteroids are small, airless rocky bodies that remain as remnants from the early formation of the solar system. They are leftover building blocks, planetesimals that never grew into planets. The majority of these objects are found within the asteroid belt, a region located between the orbits of Mars and Jupiter. Despite the high number of asteroids, numbering in the millions, the belt is mostly empty space. The distances between individual asteroids are typically vast, and spacecraft can pass through the belt without difficulty. However, gravitational perturbations from Jupiter can occasionally nudge these bodies into orbits that cross the paths of the inner planets, sending them into regions where they might one day encounter Earth or another world. Comets are characterized as icy conglomerates consisting of frozen volatiles, such as water, carbon dioxide, and ammonia, mixed with silicate dust. They are sometimes called dirty snowballs, though their exact composition varies. They typically originate in the cold, outer reaches of the solar system, in regions like the Kuiper belt beyond Neptune or the Oort cloud, a distant spherical shell of icy bodies surrounding the entire solar system. When a comet's orbit brings it close to the Sun, the increase in temperature causes the ices to sublime directly into gas, bypassing the liquid phase. This process creates a visible halo around the nucleus, called a coma, and 2 distinct tails. One tail is made of ionized gas, glowing as it is energized by sunlight, and the other is made of dust, reflecting sunlight. Both tails always point away from the Sun, pushed by solar wind and radiation pressure, regardless of the comet's direction of travel. Meteoroids are fragments of asteroids or comets ranging in size from a grain of sand to boulders. They are the small debris scattered throughout the solar system. When a meteoroid enters a planetary atmosphere at high velocity, such as Earth's, the resulting friction and compression of the air create intense heat. The air in front of the meteoroid cannot move out of the way fast enough and compresses, heating up dramatically. This produces a streak of light known as a meteor, or shooting star, as the object burns up in the atmosphere. If the object is large enough to survive the atmospheric passage, if it does not completely vaporize and strikes the surface, the remaining fragment is classified as a meteorite. These are the pieces we find on the ground. Interplanetary space is permeated by a population of microscopic dust grains produced by comet sublimation and asteroid collisions. These grains are constantly being shed and spread throughout the inner solar system. Despite the near-vacuum conditions, despite their tiny size, these grains pose a risk to spacecraft. Because spacecraft travel at orbital or escape velocities, often tens of thousands of kilometers per hour, even a grain with a mass of a fraction of a gram possesses significant energy upon impact. Speed multiplies danger. The kinetic energy can be substantial enough to puncture thin metal or damage delicate instruments. This necessitates the use of specialized shielding to protect sensitive instrumentation from these high-velocity impacts. Most artificial satellites operate within a relatively narrow region, primarily within a few Earth radii of the planet's center. This proximity facilitates high-speed data transmission, as signals do not have to travel as far, and enables high-resolution Earth observation, allowing detailed views of the surface. The majority of these objects reside in low Earth orbit, which extends up to 2,000 kilometers in altitude, a band where most satellites congregate. Others occupy higher orbits for global positioning systems, which require specific altitudes to provide coverage, or telecommunications, where geostationary positions are valuable. In the low Earth orbit environment, the atmosphere is extremely thin but not entirely absent. Even at these altitudes, there are still traces of gas, residual molecules. This residual gas exerts a force known as atmospheric drag on orbiting satellites. The drag is subtle but persistent. This drag gradually dissipates the kinetic energy of the spacecraft, removing energy from the orbit, resulting in a slow, inward spiraling decay. The orbit gets lower and lower. To maintain their altitude over long durations, satellites in this region must periodically perform station-keeping maneuvers using onboard propulsion systems, firing small thrusters to boost themselves back up. Otherwise, they eventually re-enter the denser layers of the atmosphere, where they heat up and burn up, usually disintegrating before reaching the ground. The sensation of weightlessness experienced by astronauts and equipment in orbit is not caused by an absence of gravity. This is a common misconception. Earth's gravitational pull at these altitudes remains significant, still strong enough to hold satellites and spacecraft in orbit. Instead, weightlessness occurs because a spacecraft and its occupants are in a state of continuous free fall. They are falling toward Earth, but they are also moving forward with sufficient horizontal velocity, moving sideways fast enough that they fall toward Earth along the curvature of the planet but never impact the surface. They keep missing the ground. In this frame of reference, the normal force from a floor or seat is absent. There is nothing pushing back against you. This results in an environment where objects appear to float, where liquids form spheres, and where astronauts can drift freely through the cabin. A geostationary orbit is a specific circular orbit located approximately 35,786 kilometers directly above the Earth's equator. This is a precise altitude, carefully calculated. At this altitude, the orbital period of a satellite exactly matches the Earth's rotational period, which is 23 hours, 56 minutes, and 4 seconds. This is slightly less than 24 hours, the length of a solar day. Consequently, the satellite remains fixed over a single point on the equator, hovering above the same spot as the Earth turns beneath it. This orbital characteristic is critical for television broadcasting and weather monitoring, as it allows ground-based antennas to remain pointed at a fixed location in the sky without the need for tracking hardware. The satellite appears to hang motionless in the sky. Orbital debris comprises the accumulation of human-made objects in Earth orbit that no longer serve a functional purpose. These are the remnants of decades of space activity. This includes abandoned satellite structures, their missions complete or their systems failed, discarded upper stages of launch vehicles that were jettisoned after use, and fragments generated by the breakup of larger objects, either intentional or accidental. Over decades of space flight, the concentration of these objects has increased significantly, particularly in the most heavily utilized altitude bands where satellites are most concentrated. The problem is growing worse over time. Because objects in orbit travel at velocities of approximately 7 to 8 kilometers per second, any collision between a spacecraft and orbital debris involves massive amounts of energy. At these speeds, even a fragment the size of a paint chip can strike with considerable force. The impact velocity is so high that size becomes almost irrelevant. Such impacts can puncture pressurized modules, potentially causing catastrophic decompression, shatter solar panels that provide power to the spacecraft, or disable sensitive electronics. The risk of a chain reaction of collisions, where one impact creates more debris that leads to further collisions, cascading into an exponential increase, is a theoretical scenario that remains a concern. This is sometimes called Kessler syndrome, named after the scientist who first described it. If this were to occur, certain orbital regions could become unusable for generations. In the vacuum of space, the absence of atmospheric pressure causes liquid water to undergo a rapid phase transition. According to the principles of thermodynamics, the boiling point of a liquid decreases as the surrounding pressure drops. In a hard vacuum, where pressure is nearly zero, this point falls below almost any temperature. Consequently, exposed water will simultaneously boil into vapor and, as the process of evaporative cooling removes thermal energy from the remaining liquid, that liquid may briefly freeze into ice crystals before eventually sublimating directly into gas. Water does not know whether to boil or freeze, and in a sense, it does both. The transformation is rapid and dramatic. Exposure of unprotected human tissue to a vacuum does not result in explosive decompression, despite what is often depicted in fiction. The skin and circulatory system are structurally sufficient to contain internal pressure, to keep the body intact. However, the body would undergo significant swelling as water in the soft tissues transitions to vapor, a condition called ebullism. The body would puff up noticeably. More critically, the lack of ambient pressure causes oxygen to diffuse out of the blood, moving from areas of higher pressure to lower pressure, and back into the lungs. This leads to rapid deoxygenation of the brain, starving it of oxygen. Loss of consciousness typically occurs within 10 to 15 seconds. Without rescue and repressurization, death would follow shortly after. The vacuum itself does not kill instantly, but the effects are swift and severe. Thermal management is a primary engineering challenge for spacecraft because of the extreme temperature gradients encountered in a vacuum. Without an atmosphere to distribute heat, to even out temperatures, a surface facing the sun can reach temperatures exceeding 120 degrees Celsius as it absorbs intense solar radiation, unfiltered by any atmosphere. At the same time, a surface in shadow can plunge to minus 150 degrees Celsius as it radiates heat into the cold sink of space, with nothing to warm it. These extremes can exist just meters apart on the same spacecraft. This necessitates the use of sophisticated materials and insulation to maintain the structural integrity of internal components, to keep instruments and electronics within their operational temperature ranges. Spacecraft regulate their internal environment primarily through the balance of radiation. Because other methods of heat transfer, conduction and convection, are unavailable in a vacuum, excess heat generated by electronics and life support systems must be moved to external radiators. These radiators are panels that extend from the spacecraft, positioned to face away from the sun. There, the heat is emitted into space as infrared radiation, invisible but essential. Conversely, thermal coatings and insulation, such as multi-layer insulation blankets or specialized paints with carefully chosen reflective properties, are used to control the amount of solar energy the craft absorbs. White surfaces reflect light and stay cooler, while black surfaces absorb energy and warm up. By balancing what comes in with what goes out, engineers ensure the vehicle remains within a specific thermal range. To sustain human life in the vacuum of space, spacecraft and habitats must be equipped with pressurized life support systems. These systems maintain an internal pressure equivalent to or near Earth sea level, creating an artificial atmosphere. They supply a continuous stream of breathable oxygen, replacing what is consumed by breathing. They remove metabolic waste products, primarily carbon dioxide exhaled by the crew, as well as water vapor and trace contaminants. Carbon dioxide must be scrubbed from the air, as it would otherwise build up to dangerous levels. Additionally, these systems must actively circulate the air to prevent pockets of exhaled gas from accumulating around the crew in a weightless environment. In microgravity, air does not rise or fall. It must be pushed. A spacesuit, formerly called an extravehicular mobility unit, acts as a self-contained, person-shaped spacecraft. It is a miniature life support system wrapped around a single human. It provides a pressurized oxygen environment to prevent the conditions that would occur in a vacuum, including ebullition and hypoxia, the lack of oxygen. It includes multiple layers of specialized fabrics, each serving a different function. The outer layers are designed to be puncture-resistant to guard against micrometeoroids, tiny but fast-moving particles that could breach the suit. They are treated to reflect a portion of the high-intensity ultraviolet radiation encountered outside the atmosphere, which is far stronger than what reaches the ground. Inside these layers are insulation to manage temperature and an airtight bladder to hold pressure. The suit is complex, expensive, and essential for survival outside the spacecraft. The space environment is permeated by ionizing radiation, which consists of particles or photons with sufficient energy to displace electrons from atoms or molecules. This process can damage chemical bonds, including those in DNA, potentially causing mutations or cell death. This radiation originates from three primary sources. First, the steady solar wind, the continuous stream of particles from the Sun. Second, sporadic solar particle events, which are eruptions from the Sun called flares or coronal mass ejections, sending bursts of high-energy particles into space. Third, galactic cosmic rays from distant supernova remnants, particles that have traveled across interstellar space. Unlike visible light, which can be easily blocked, this high-energy radiation can penetrate many materials, requiring thick shielding or specialized materials to stop it. It poses a long-term health risk to humans on extended missions and can cause potential bit flips or damage to sensitive electronic microchips, where a single particle can flip a 0 to a 1 or vice versa in computer memory. Earth's surface is uniquely protected from the harshest elements of space radiation by two primary shields working in concert. The magnetosphere and the atmosphere cooperate to create a safe environment. The planet's magnetic field deflects the majority of charged particles from the solar wind and cosmic rays, bending their paths away or trapping them in regions called the Van Allen radiation belts, where they spiral back and forth along field lines. Any particles or high-energy photons that penetrate the magnetic shield must then pass through the dense layers of the atmosphere, which further reduce the radiation through collisions with gas molecules. Each collision removes energy, and by the time radiation reaches the surface, most of it has been absorbed. This layered protection makes life on the surface viable, shielding us from conditions that would otherwise be lethal. Astronauts in orbit are subjected to significantly higher levels of radiation than individuals on the ground. They reside above the protective density of the atmosphere, where there is no air to shield them, and in some cases, outside portions of the magnetosphere when their orbits take them through the Van Allen belts or above them. This exposure includes a higher flux of heavy ions, charged particles with significant mass and energy, and secondary radiation produced when cosmic rays strike the spacecraft hull. Even the walls of the spacecraft can produce radiation when struck by high-energy particles. Space agencies strictly monitor the cumulative radiation dose of every astronaut, tracking exposure over their entire career to ensure that their long-term risk of radiation-induced illness remains within acceptable safety limits. Missions to the Moon or Mars would involve even higher exposure. Space-based telescopes operate outside the Earth's atmosphere, which eliminates the distortion caused by atmospheric turbulence. On Earth, the atmosphere is constantly in motion. Shifting pockets of air with varying temperatures and densities cause starlight to bend unpredictably as it passes through. This phenomenon is known as astronomical seeing, and it results in the twinkling of stars that we observe on a clear night. While charming to watch, this twinkling represents a blur, a distortion that limits the sharpness of images. By positioning observatories in the vacuum of orbit, above the atmosphere entirely, astronomers can achieve significantly sharper images than most terrestrial facilities. The telescope can reach its theoretical limit, determined only by the size and quality of its optics, not by the air above it. The Earth's atmosphere acts as a selective filter, blocking large portions of the electromagnetic spectrum. While visible light and some radio waves reach the surface through what are called atmospheric windows, transparent regions where light can pass, most ultraviolet, X-ray, and gamma-ray radiation is absorbed by the ozone layer and other atmospheric gases high above. These wavelengths never reach the ground. Similarly, much of the infrared spectrum is blocked by water vapor and carbon dioxide in the air, which absorb these wavelengths efficiently. Space-based observatories, such as the James Webb Space Telescope or the Chandra X-ray Observatory, are essential for observing these wavelengths. They provide data on high-energy cosmic events and the obscured interiors of star-forming regions, places hidden from view in visible light. They reveal what ground-based telescopes cannot see. To mitigate the blurring effects of the atmosphere, modern ground-based observatories utilize adaptive optics. This is a sophisticated technology that works in real time to correct distortions. It employs sensors to measure atmospheric turbulence as it occurs, sampling the air hundreds of times per second. Often, these systems use a laser to create an artificial reference point, a bright spot in the upper atmosphere that acts like an artificial star. Computers then calculate the necessary corrections based on how this reference point appears distorted, and they rapidly adjust the shape of a deformable mirror. This mirror can change its surface shape, sometimes hundreds of times per second, bending in precise ways to cancel out the distortion introduced by the atmosphere. While highly effective at improving resolution in the infrared and visible bands, allowing ground telescopes to compete with space-based ones in certain wavelengths, adaptive optics cannot compensate for the total absorption of certain wavelengths by the atmosphere. Some light simply never arrives, and no correction can retrieve what isn't there. Astronomical distances are determined through a tiered system of measurement techniques known as the cosmic distance ladder. This is sometimes called the distance scale. Because direct measurement with physical probes is impossible beyond the solar system, we cannot simply send a spacecraft to measure the distance. Astronomers rely on a progression of indirect methods where each step calibrates the next. These methods build upon each other, each extending our reach further. They include geometric measurements for nearby stars, where we can use trigonometry. For intermediate distances, astronomers use luminosity-based measurements employing what are called standard candles, objects with known brightness. For the most distant galaxies, they use observations based on the expansion of the universe, measuring redshift. Each rung of the ladder depends on the accuracy of the previous rung. Stellar parallax is the only direct geometric method for measuring the distance to stars beyond the solar system. It is the foundation of the distance ladder. It relies on observing the apparent displacement of a nearby star against a background of much more distant objects as the Earth moves from one side of its orbit to the other, traveling across the diameter of Earth's orbit over 6 months. By measuring this tiny angular shift, which is incredibly small, and knowing the radius of Earth's orbit precisely, astronomers can use basic trigonometry to calculate the star's distance. The closer the star, the larger the shift. The farther the star, the smaller the shift, until at great distances, the shift becomes too small to measure even with the most sensitive instruments. The unit parsec is derived directly from this method, making it a natural unit for stellar distances. Standard candles are a class of astrophysical objects that possess a known, consistent intrinsic brightness. They shine with a predictable luminosity. By comparing this known brightness to the object's apparent brightness as measured from Earth, how dim it appears to us, astronomers can apply the inverse square law of light to calculate the distance to the object. Light spreads out as it travels, weakening with distance. The reliability of this method depends on the accuracy with which the standard nature of the object's brightness is understood and calibrated. If the assumption of standard brightness is wrong, the distance calculation will be wrong. This is why finding reliable standard candles has been so important in astronomy. Cepheid variable stars serve as critical standard candles for measuring distances within the Milky Way and out to nearby galaxies. These are stars that pulse, brightening and dimming in a regular cycle. These stars exhibit a direct relationship between their period of pulsation and their intrinsic brightness. The longer the period, the brighter the star. Larger, brighter Cepheids pulsate more slowly than smaller, dimmer ones, taking weeks to complete a cycle compared to days for smaller ones. By measuring the time it takes for a Cepheid's brightness to cycle from bright to dim and back to bright, astronomers can determine its absolute magnitude, its true brightness. Once they know how bright it really is, and they can see how bright it appears, they can subsequently calculate how far away the host galaxy must be. Cepheids have been used to map distances across millions of light-years. Type Ia supernovae are utilized as standard candles for mapping the largest cosmological scales. These are some of the brightest standard candles known. These events occur in binary star systems when a white dwarf, the remnant of a dead star, accretes enough matter from a companion star to reach a specific mass limit, known as the Chandrasekhar limit. When this threshold is crossed, the white dwarf can no longer support itself, and it triggers a thermonuclear explosion with a very predictable peak brightness. Because the conditions are always similar, the explosions are always similar in brightness. Because these explosions are incredibly bright, they can be seen across billions of light-years, visible across a substantial fraction of the observable universe. Observations of type Ia supernovae in the late 20th century were instrumental in the discovery that the expansion of the universe is accelerating, a finding that surprised astronomers and pointed to the existence of dark energy. Spectroscopy is the study of the interaction between matter and electromagnetic radiation. It is one of the most powerful tools in astronomy. It provides a wealth of information about celestial bodies that images alone cannot reveal. A picture shows shape and brightness, but spectroscopy reveals composition and motion. By dispersing light into its constituent wavelengths to create a spectrum, spreading it out like a rainbow, astronomers can identify specific absorption and emission lines. These are dark or bright lines at particular wavelengths. These spectral fingerprints allow for the determination of an object's chemical composition, revealing which elements are present. They also reveal the object's surface temperature, the pressure within its atmosphere, and its magnetic field strength. Almost everything we know about the physical properties of stars comes from spectroscopy. The position of spectral lines within a spectrum shifts according to the relative motion between the observer and the source. If an object is moving away from the observer, receding into the distance, its light is stretched. This shifts the spectral lines toward the longer, redder wavelengths. This is known as redshift. Conversely, if an object is approaching, moving toward the observer, the light is compressed, squeezed. This shifts the lines toward shorter, bluer wavelengths, known as blue shift. The magnitude of this shift is directly proportional to the velocity of the object along the line of sight, the speed at which it is moving toward or away from us. Larger shifts indicate higher velocities. The Doppler effect for light is the physical principle behind the shifting of spectral lines due to motion. By measuring the precise displacement of known spectral lines, such as those of hydrogen or calcium, elements whose spectral fingerprints are well catalogued, astronomers can calculate the radial velocity of stars and galaxies. This data is essential for mapping the rotation of galaxies, revealing how fast different parts are spinning. It is used for detecting the subtle motion of stars caused by orbiting planets, the small wobble induced by a planet's gravity. And it confirms the large-scale expansion of the cosmic web, showing that distant galaxies are moving away from us. The Doppler effect allows us to measure motion across the universe. A significant proportion of stars do not exist in isolation but are instead part of binary or multiple star systems. Many stars have companions. In a binary system, two stars are gravitationally bound and orbit a common center of mass, circling each other over time. These systems range widely. Wide binaries have stars separated by thousands of astronomical units, so far apart that they barely influence each other. Closed binaries have stars separated by only a few stellar diameters, orbiting rapidly. In some cases, contact binaries exist, where the stars are so close they share a common envelope of gas, touching each other. Multiple star systems can contain 3 or more stars, often organized in hierarchical orbits to maintain gravitational stability over cosmic timescales. A pair might orbit close together, with a third star orbiting the pair at a greater distance. Exoplanets are planetary bodies that orbit stars outside of our solar system. They are worlds around other suns. Since the first confirmed discovery in the 1990s, a finding that opened a new chapter in astronomy, thousands of these worlds have been identified. The number continues to grow as detection methods improve. This has revealed a vast diversity in planetary architecture, far greater than what exists in our own solar system. These include what are called hot Jupiters, gas giants that orbit extremely close to their parent stars, completing an orbit in just a few days. There are also super-Earths, planets with masses between those of Earth and Neptune, a category that does not exist in our solar system. The study of exoplanets is critical for understanding the frequency of planetary systems throughout the galaxy and the conditions necessary for habitability, for determining how common Earth-like worlds might be. The identification of exoplanets relies primarily on indirect detection methods. We cannot usually see these planets directly. The light from the parent star typically overwhelms the faint reflection of a planet, like trying to see a firefly next to a spotlight. One technique involves monitoring a star's brightness over time, watching for subtle changes. If a planet's orbit is aligned such that it passes in front of the star from Earth's perspective, creating what is called a transit, it causes a periodic, measurable dip in the star's light. The star dims slightly, then returns to normal brightness. By observing these repeating dips, astronomers can infer the presence of a planet. Another method detects the subtle gravitational motion of a star as it is pulled by an orbiting planet. The planet tugs on the star, causing the star to wobble slightly. This causes the star's spectral lines to shift back and forth, alternating between redshift and blueshift as the star moves toward and away from us. By combining data from different detection methods, astronomers can characterize the physical nature of an exoplanet. Each method reveals different information. One method provides the planet's radius, its size, by measuring how much light is blocked during a transit. Another method provides its mass, or at least a minimum mass, by measuring how much the star wobbles. When both values are known, the average density of the planet can be calculated. Density is mass divided by volume. This density value is fundamental for distinguishing between different planetary compositions, allowing researchers to determine if a world is likely rocky like Earth, with a solid surface, gaseous like Jupiter, with no solid surface at all, or perhaps an ocean world with a high proportion of water and volatiles. Different compositions produce different densities. Launching a spacecraft from the Earth's surface involves the expenditure of significant energy. It is one of the most energy-intensive activities humans undertake. The spacecraft must overcome the planet's gravitational pull, which wants to hold it down, and the resistance of the atmosphere, which creates drag. To reach orbit, a launch vehicle must achieve a specific velocity, approximately 7.8 kilometers per second for low Earth orbit, while simultaneously ascending through the denser layers of the atmosphere. During the initial phase of flight, as the rocket accelerates and climbs, atmospheric drag creates pressure on the vehicle. There is a moment of maximum aerodynamic pressure, called max Q, which occurs as the rocket passes through the denser lower atmosphere at high speed. This requires structural resilience and specialized aerodynamic shaping to minimize energy loss and prevent the vehicle from being torn apart. Because the mass of propellant constitutes a large percentage of a spacecraft's total weight, often 90% or more, mission planners utilize high-efficiency trajectories to conserve fuel. Every kilogram of fuel saved can mean more payload delivered. This involves the strategic timing of launch windows to align with planetary positions, launching when Earth and the destination are favorably positioned. By optimizing these paths, missions can maximize payload capacity, carrying more instruments or supplies, and extend the operational lifespan of the spacecraft, ensuring enough fuel remains for the mission's duration. Gravitational assist maneuvers are used to alter the velocity and trajectory of a spacecraft without the consumption of onboard fuel. This is a clever technique that borrows energy from planets. When a spacecraft passes through the sphere of influence of a planet, the region where that planet's gravity dominates, it exchanges orbital energy with that planet. The planet's gravity pulls the spacecraft, changing its speed and direction. Depending on the geometry of the approach, whether the spacecraft swings past in front of or behind the planet in its orbit, the spacecraft can gain or lose speed relative to the Sun and change its flight path significantly. The planet loses or gains a tiny amount of orbital energy in return, but because planets are so massive, the effect on them is negligible. This technique was essential for missions to reach the outer solar system, allowing spacecraft like Voyager and Cassini to build up enough speed to journey to distant worlds. Ion propulsion is a form of electric propulsion that generates thrust by accelerating ionized gas through an electric field. Typically, the propellant used is xenon, a heavy, inert gas. While the total thrust produced is very low, comparable to the weight of a sheet of paper resting on your hand, the exhaust velocity is significantly higher than that of chemical rockets. The particles are ejected at tremendous speeds. This high efficiency means that ion engines can operate continuously for months or years, slowly building up velocity over time. This makes them highly efficient for long-duration deep space missions where fuel mass is a critical constraint, where carrying enough chemical fuel would be impractical. Reaction control systems are small thruster blocks distributed around a spacecraft. They are used to manage its orientation in space and perform fine maneuvers. These thrusters provide short, precise bursts of force, little puffs of propellant expelled in specific directions. By expelling mass in one direction, the spacecraft rotates or moves in the opposite direction. This allows the spacecraft to rotate around its center of mass, changing which way it points, or to perform the delicate procedures required for docking with another spacecraft, such as the International Space Station. Without these systems, a spacecraft could not point its instruments or align itself for critical operations. In the environment of deep space, far from significant gravitational sources or atmospheric interference, a spacecraft adheres to Newton's first law of motion. In the absence of an external force, an object in motion remains in uniform motion at a constant velocity. Once a spacecraft has completed its initial propulsion burn and reached its cruise velocity, it will continue along its trajectory indefinitely without requiring further engine operation. It coasts through the void, conserving its momentum. The engines can be shut off, and the spacecraft continues. Only when a change in velocity is needed to adjust course or slow down at a destination are the engines fired again. The propulsion of all spacecraft is governed by the law of conservation of momentum. Momentum must be conserved in any closed system. To gain momentum in a forward direction, a spacecraft must expel a portion of its mass in the opposite direction at high velocity. This is the principle of the rocket. The change in the spacecraft's velocity is directly related to the mass of the propellant expelled and the velocity at which it leaves the engine. Expelling more mass, or expelling it faster, produces more change in velocity. This is described by the rocket equation, formulated long ago but still fundamental to space travel. Inertial navigation systems allow a spacecraft to track its position and velocity autonomously, without needing to observe external references. These systems utilize a combination of accelerometers, which measure linear acceleration, and gyroscopes, which measure angular velocity and orientation. By integrating these measurements over time, adding up all the small changes, the onboard computer can calculate the spacecraft's current state relative to its starting point. This process is known as dead reckoning. While highly useful, these systems accumulate small errors over time, so periodic corrections using external observations are often needed to maintain accuracy. Star trackers are high-precision optical instruments used to determine the orientation of a spacecraft in three-dimensional space. The device captures images of the surrounding star field, taking pictures of the stars visible in its field of view. It then compares the observed patterns against an onboard star catalog using pattern recognition algorithms, matching the observed arrangement to known star positions. Because the positions of stars are fixed and well-mapped, unchanging over human timescales, star trackers provide an accurate method for ensuring a spacecraft's instruments or communication antennas are pointed in the correct direction. They tell the spacecraft which way it is facing. Radio communication between Earth and spacecraft is fundamentally constrained by the constant speed of light. Because signals must traverse immense distances, traveling at the fastest possible speed but still requiring time, a significant delay occurs between the transmission of a command and its receipt by the spacecraft. There is also a delay for the return of data to Earth. This is called the one-way light time, the time it takes for a signal to make the journey. This delay increases as a spacecraft moves further from the planet. For missions at Mars, depending on where Mars is in its orbit relative to Earth, the delay can range from 4 to 24 minutes. For a probe in interstellar space, like Voyager, the delay exceeds 22 hours. This latency necessitates high levels of onboard autonomy. The spacecraft must be able to make decisions on its own. Real-time remote control is physically impossible when the round-trip delay can be hours. The intensity of a radio signal emitted by a spacecraft follows the inverse square law as it propagates through the vacuum. As the signal travels away from the spacecraft, spreading outward in all directions, it forms an expanding sphere. As the spherical wavefront of the signal expands, growing larger with distance, the power is distributed over a surface area that increases with the square of the distance from the source. Consequently, doubling the distance from a spacecraft reduces the received signal strength to 1/4 of its previous level. Triple the distance, and the signal becomes 1/9 as strong. To compensate for this reduction over interplanetary distances, where signals must travel millions or billions of kilometers, space agencies utilize extremely large ground-based parabolic antennas. These massive dishes, such as those in the Deep Space Network, which has stations positioned around the globe, are designed to capture the faint signals, collecting as many photons as possible from the weak microwave transmissions arriving from distant spacecraft. Tracking the position and velocity of a spacecraft relies on the precise measurement of radio signal characteristics. Two primary methods are used. By measuring the time it takes for a signal to complete a round trip between Earth and the spacecraft, traveling out and back, engineers can determine the exact distance to within meters. This is called ranging. The signal is sent with a specific timing code, and when it returns, the delay reveals the distance. Simultaneously, the Doppler effect causes the frequency of the radio signal to shift based on the spacecraft's relative motion. If the spacecraft is moving toward Earth, the frequency increases slightly. If moving away, it decreases. This allows for the calculation of the spacecraft's velocity with precision. These measurements are synchronized using ultra-stable atomic clocks, the most accurate timekeeping devices available, to maintain accuracy over long-duration missions. Small timing errors would accumulate into large errors in position. The trajectories of spacecraft and the orbits of planetary bodies are predicted using numerical calculations. Computers perform these calculations iteratively. Because the solar system is a multi-body system where every mass exerts a gravitational influence on every other mass, the Sun pulling on the planets pulling on each other and on their moons, there is no simple solution for their exact positions over long periods. The mathematics becomes intractable. Instead, computers perform step-by-step calculations, advancing time in small intervals. They sum the gravitational forces from the Sun, planets, and major moons at each time step, calculating how these forces change the velocity and position of each object. This allows mission navigators to account for subtle perturbations, small tugs from distant bodies, and plan the precise engine burns required for orbital insertion around a planet or for encounters with specific targets. The physical universe is governed by four fundamental interactions that dictate the behavior of all matter and energy. Everything that happens, at every scale, is the result of these four forces. These are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. While gravity and electromagnetism have an infinite range and are the primary forces observed at astronomical scales, shaping galaxies and governing the motion of planets, the strong and weak forces operate only within the subatomic distances of the atomic nucleus. They are confined to incredibly small scales. The relative strengths and ranges of these four forces determine everything from the stability of atoms, why matter holds together, to the formation of the largest galaxy structures, why the universe looks the way it does. Electromagnetism is the force responsible for all interactions between electrically charged particles. It governs how charged particles attract or repel each other. In the context of space, it governs the propagation of light, which is itself an electromagnetic wave, and the dynamics of charged particles within planetary magnetospheres and the solar wind. Because this force is significantly stronger than gravity at a microscopic level, far stronger when comparing individual particles, it controls the structure of atoms and molecules, holding electrons in orbit around nuclei. On cosmic scales, however, electrical neutrality often prevails. Positive and negative charges tend to balance out over large regions. This allows gravity, though weaker, to dominate the motion of massive bodies like stars and galaxies, which are electrically neutral overall. The strong nuclear force is the most powerful of the fundamental interactions. It is far stronger than the other forces, but only at very short range. It is responsible for binding protons and neutrons together within the atomic nucleus. This force must be strong enough to overcome the intense electromagnetic repulsion between positively charged protons, which would otherwise push each other apart. Like charges repel, but the strong force overpowers this repulsion when particles are close enough. In the hearts of stars, the strong force is the mechanism that allows nuclear fusion to occur. When hydrogen nuclei are forced close enough together by the extreme pressure and temperature of the stellar core, the strong force takes over, binding them together. They fuse into helium, and this process releases the energy that powers the star, that makes stars shine. The weak nuclear force is responsible for certain processes of radioactive decay. It is much weaker than the strong force and operates over even shorter distances. It governs transformations within the nucleus, such as when a neutron transforms into a proton while emitting an electron and an antineutrino. This is called beta decay. This interaction is essential for the processes that occur in stars, as it facilitates the conversion of particles during fusion reactions. Without the weak nuclear force, the chains of reactions that power the Sun would not proceed at the correct rate. The Sun would be unable to produce the steady stream of energy required to support life on Earth. The weak force, though subtle, is necessary for stellar stability. While matter on Earth is commonly found in solid, liquid, or gaseous states, the forms we encounter daily, the vast majority of ordinary matter in the observable universe exists as plasma. Plasma is the fourth state of matter. It is a state in which a gas has been energized until its atoms lose their electrons, breaking apart. This results in a collection of free-floating ions, atoms with missing electrons, and electrons moving independently. From the interiors of stars, where temperatures reach millions of degrees, to the thin intergalactic medium spread between galaxies, this ionized gas is the dominant phase of matter in the cosmos. Stars are made of plasma. The space between stars often contains plasma. It is the most common state. Because plasma consists of free charged particles, it is highly conductive. Electric currents can flow through it easily. It responds dynamically to electromagnetic fields. Unlike neutral gases, which are not affected much by magnetic fields, plasmas are strongly influenced. Plasmas are sometimes said to be frozen to magnetic field lines, meaning the motion of the particles and the orientation of the magnetic fields are intrinsically linked. Where the field goes, the plasma tends to follow. This interaction leads to complex phenomena, such as magnetic reconnect ion, where magnetic field lines that are oppositely directed come together, snap, and realign in a new configuration. When this happens, magnetic energy is suddenly converted into kinetic energy and heat, releasing massive amounts of energy. This process powers solar flares and auroral displays. Shock waves in space occur when the flow of a plasma exceeds its local signal speed, faster than information can propagate through the medium. This is analogous to a sonic boom when an aircraft exceeds the speed of sound in air. A prominent example is the bow shock, which forms where the supersonic solar wind first encounters the boundary of a planet's magnetosphere. The solar wind, streaming outward from the Sun at hundreds of kilometers per second, suddenly meets an obstacle. At this shock front, the plasma is abruptly decelerated, slowed down. It is compressed, packed more tightly, and heated to much higher temperatures. The kinetic energy of the flowing wind is converted into thermal energy and magnetic energy. The result is a standing wave in space, a region where conditions change sharply. Large-scale magnetic fields are a pervasive feature of the universe. They are found threading through stars, galaxies, and even the vast gaps within galaxy clusters. These fields are often generated by processes called dynamos, where the motion of conductive fluids creates and sustains a magnetic field. In planets, molten iron in the core circulates, driven by heat and rotation. In stars, plasma circulates in complex patterns. These motions, combined with the conductivity of the material, generate magnetic fields. On a galactic scale, these fields influence the rate of star formation, as magnetic pressure can resist the collapse of gas clouds. They also influence the propagation of high-energy cosmic rays, bending their paths and containing them within the galaxy for longer periods. Turbulence is a fundamental characteristic of astrophysical plasmas. It is characterized by chaotic, multi-scale fluctuations in velocity and magnetic field strength. Eddies within eddies, patterns within patterns. This turbulence plays a role in the cosmic ecosystem by facilitating the transport of heat and energy across vast distances, mixing hot and cold regions. It also assists in the diffusion of magnetic fields, spreading them throughout a medium, and regulates the motion of charged particles. Turbulence effectively acts as a cosmic mixer, stirring the contents of space. It distributes elements and energy throughout the interstellar and intergalactic media, ensuring that the products of stellar nucleosynthesis are spread widely rather than remaining concentrated. Scientific observations and experiments consistently demonstrate that the laws of physics established on Earth are universal. They apply everywhere, at all times. The conservation of energy and momentum, the fundamental accounting rules of the universe, hold true everywhere. The laws of thermodynamics, governing heat and entropy, operate the same way in distant galaxies as they do here. The principles of special and general relativity, describing motion and gravity, have been tested and verified across billions of light-years. By observing the behavior of distant objects, astronomers confirm that the fundamental constants of nature, numbers like the speed of light and the strength of gravity, remain consistent throughout the observable universe. The universe plays by the same rules everywhere. As this quiet journey comes to a close, you can allow the remaining words to fade into the background. Thank you for spending this time with the Curious Owl. Among all the voices and sounds available, your choice to be here is deeply appreciated. If you'd like, you're welcome to return again, and to share what felt calming, or what could be softened even further. Your presence helps shape this space. For now, there's nothing more to consider. The world continues at its own gentle pace, and you're free to rest within it. Good night.